Hello students, how are you? Make sure the screen is visible to you and I'm audible to you. So student of JEE Main, am I audible to you? Screen is visible to you? Let me know in the chat box if it is so. I have also launched the poll. Please do participate in that. So in today's session, we are going to revise this chapter named Modern Physics, in which we conclude all the details and that is very important for the upcoming exam. And we will also solve some PYQs, okay, based on previous years of JEE Main. Okay. So in modern physics, there are three chapters: atom, nuclei, and dual nature of matter. All three chapters are comprises into one unit, which is modern physics. Okay. Now the important part of these chapters are like we are going to discuss. We are going to discuss through the questions. Okay. Now the very first question to your screen is this. I hope the screen is visible to you, as you are not responding, so that's why I'm considering that screen is also visible to you. Now, UV light of 4.13 electron volt is incident on a photosensitive metal surface having work function as 3.13 electron volt. The maximum kinetic energy of ejected photoelectron will be. So first of all, this question is from the photoelectric effect. We know that in photoelectric effect, we have a sensitive metal. Here we will have a sensitive metal. And this sensitive metal is exposed to different kind of waves or different kind of light waves or electromagnetic waves. These waves are capable of ejecting electron from this surface. This phenomena is termed as the photoelectric effect. So here the UV light is coming in this way and it ejects out some electron from this sheet, from this metal. Now we know that to eject out the electron from a sensitive metal, we need to overcome the work function of that metal. Now, what is work function? Which is also mentioned in this question, work function. The work function is the minimum amount of energy that an electron will require to eject it out from the metal surface. Or it is the kind of energy that we require to eject out the electron, the minimum energy that we require. And it is varies for metal to metal. As metal changes, the work function will also change. So work function is the minimum amount of minimum amount of energy to eject out the electron from the metal surface, from metal surface. Now we know that here the work function is given as 3.13, which means at least that much amount of energy we should have. Okay, but the light that is falling on the surface having 4.13 electron volt of energy, which means it is exceeding the work function of the metal. Now there is a very famous equation which is given by Sir Albert Einstein, is nothing but that kinetic energy maximum is equals to the energy that a light is carrying or incident light is carrying minus the work function of the metal. Now this h is the Planck constant, this nu is the frequency here. This work function can also be written as h nu naught. Okay, this is kinetic energy max. Now here in this question it is being asked that what is the maximum kinetic energy of ejected photoelectron. So kinetic energy max equals to h nu, which is nothing but the totally it is saying about the energy. So energy of incident ray is 4.13 electron volt minus work function is also given in electron volt. No need to convert the unit. This is 3.13 electron volt. Now 4.13 minus 3.13 will become 1 electron volt. This is kinetic energy max. ठीक है ना? So 1 electron volt will be the maximum kinetic energy of the ejected photoelectrons. It does not mean that all the electrons possess this maximum kinetic energy. It does not mean that. Okay. Answer is 2. I hope you got this answer. Anyone, if you have any doubt, you can ask right now over the chat box, or you can unmute yourself and then also ask whatever the doubt you have. Now, move on to the next question. This one. Now here, the minimum energy required by a hydrogen atom in ground state to emit radiation in Balmer series is nearly. First of all, we should know that what is the energy and how it depends on the number of shells. Okay, because this Balmer, Paschen, Lyman, these are the series that we have in hydrogen spectrum. So for that, we have to identify that Balmer series is nothing but for n is equals to 2, where n is the level of state. Okay. Now, for ground state, we know. Here I'm drawing this. For ground state, n is equals to 1. This is n is equals to 2, n is equals to 3, n is equals to 4, and there is n is equals to 5, 6, and further. But you should know that for n is equals to 1, these are the number of n means shell. So from one shell to second shell to third shell, fourth shell, in which electrons are revolving. Now, the energy of n is equals to 1 level is minus 13.6 electron volt. And although you can relate it with energy is directly proportional to or is equals to minus 13.6 upon n square electron volt. We just need to put the value of n to get the energy. Now, but Balmer series start from n is equals to 2. Okay. If a series is starting or the electron is making transition from n is equals to 2 to 1 or from any state to ground state, always remember, from any state to ground state, that is nothing but the spectrum line will be categorized as Lyman series. Lyman series. But from any state, if the electron is electron taking the transition or changing the state, from any state to n is equals to 2, any above state, that series that you will have, or that spectral line series you will have, is categorized as Balmer series. These are the Balmer series. After that, same procedure for n is equals to 3, from any state to n is equals to 3, we will have a Paschen series. Paschen series. And for n is equals to 4, we will have bracket series. And for n is equals to 5, we will have the P fund series. Okay. And there is another formula to relate the energy and to calculate the energy. E is equals to minus 13.6 n square. Now we know that for Balmer series n is equals to 2, and that will be the minimum energy required. Okay. So minimum energy required for this transition only, which is happening from state 3 to 2. But for Bauman series, we need to put n is equals to 2, because ultimately the spectral line that we are getting for n is equals to 2 state. So when we put n is equals to 2, this will become 4, and this will approximately coming out as 1.5 electron volt minus, which means this is a negative energy. Negative energy means that whatever the electron is revolving in this state is stable, because energy is negative. So to remove that electron, okay, or to make the radiation in that particular series, we need at least this much amount of energy, which is minus 1.5 electron volt. Ka opposite, which will be plus 1.5 electron volt. मैक्सिमम तो आप कितना भी दे सकते हैं ना, मिनिमम इज दिस अमाउंट. ओके. लाइक अगर वो बोलता है आपसे व्हाट इज द एनर्जी रिक्वायर्ड, minimum energy required by a hydrogen atom in ground state to emit radiation in Balmer series, nearly तो ये हो गया. For Paschen series, that will be n is equals to 3. For ground state, तो n is equals to 1, which means किसी भी इलेक्ट्रॉन को ग्राउंड स्टेट से बाहर completely इजेक्ट आउट कराने के लिए how much energy we required, which is minus 13.6, means plus 13.6 energy we required to eject out the electron. Same is this, we can take here. Energy of state 1 is minus 13.6. Energy of state 2 is minus 3.4 electron volt. Energy of 3 is minus 1.5 electron volt. Okay. Just a second. Okay. So this is the energy of n is equals to 3 minus 1.5 electron volt, and this energy here is 3.4 electron volt minus 3.4, and for 1 is minus 13.6 electron volt. Now, to make, now just understand the question here. The minimum energy required by a hydrogen atom in ground state to emit radiation in Balmer series. अब Balmer series तो n is equals to 2 से स्टार्ट होगी, तो कोई भी रेडिएशन अगर यहाँ के लिए एमिट करना है तो एटलीस्ट इलेक्ट्रॉन को इस स्टेट में तो आना पड़ेगा. मतलब दिस मच अमाउंट ऑफ डिफरेंस ऑफ एनर्जी इट रिक्वायर्ड. ठीक है. फ्रॉम ग्राउंड स्टेट टू दिस, ग्राउंड स्टेट से इस स्टेट में कितना ट्रांजिशन करेगा, वो एनर्जी का डिफरेंस. Got it? So for the radiation emission of Balmer series, we need this much amount of difference of energy, which is nothing but minus 13.6 minus 1.5 इलेक्ट्रॉन वोल्ट. नाउ क्योंकि बामर सीरीज में रेडिएशन करने के लिए एटलीस्ट इसे स्टेट नंबर 3 से तो जंप करना पड़ेगा मिनिमम, तभी तो बामर सीरीज में आएगा. इसलिए वी नीड दिस मच अमाउंट ऑफ डिफरेंस ऑफ एनर्जी, ताकि हम क्या करेंगे, इलेक्ट्रॉन को, दिस इज द इलेक्ट्रॉन, वी शूट अप दिस इलेक्ट्रॉन फ्रॉम ग्राउंड स्टेट टू 1 2 3 3 स्टेट में. फिर ये वापस से आएगा, तो ये जो ट्रांजिशन होगा ये बामर सीरीज में होगा. ठीक है. So that is why the difference of energy that we required is minus 13.6 to minus of minus 1.5, which is 12.1 electron volt. So minimum energy required is magnitude of this 12.1 electron. Option C. Now, if the wavelength of first member of Lyman series of hydrogen is lambda, the wavelength of second member will be. The very famous formula to calculate wavelength is 1 upon lambda into equals to R 1 upon n1 का स्क्वायर minus 1 upon n2 square. Now, suppose for this question Lyman series we are taking it. So Lyman series is nothing but for the ground state to the uppermost state. So the very first member of Lyman series, for that n1 will become n1 because transition is happening to 1, so n1 will always remain 1. n2 is the final excited state. n2 for first member it will be like this. So from n1 to n2. So for first member n1 will become 1 and n2 will become 2. For second member n1 will remain 1, n2 will become 3, and so on. This is for the first member. And this is for the second member. Now, for first member it is already given as 1 upon lambda. We can calculate 1 upon lambda, 1 upon 1 square minus 1 upon 2 square. 1 upon lambda is equals to 1 minus 1 upon 4. 1 upon lambda is equals to 4 minus 1 by 3 by 4 into R also. So 1 upon lambda here is 3 upon 4R. So lambda will become 4 upon 3R. This is equation 1. Now for the second member, as this has been asked in the question, second member, we will put up the value here, 1 upon 1 square minus 1 upon 3 square. Now 1 upon lambda, R is also there. R is nothing but the Rydberg constant. R 1 minus 1 upon 9. 1 upon lambda, this will be 9 minus 1 is 8. This will become 8R upon 9. So lambda 2, I will write it as lambda 2 and this one is lambda 1. Lambda 2 is nothing but 9 upon 8R. Now we have to make here lambda 1, which is 4 upon 3R. So what we can do, we can just multiply by 4 by 3. And multiply with the inverse also. Now, this 4 by 3R will become lambda 1, which is nothing but lambda. 9 3s are 27 by 8 4s are 32 into lambda. So this is the relation between the first member of Lyman series to the second member of Lyman series. Now, Some more specification about Lyman series I will give you in the next sheet. Now, this series, the Lyman series lies in UV region. So you should always remember that Lyman series always lies in UV region. Okay. Now, if he will ask you about the longest wavelength of Lyman series. So for longest wavelength of Lyman series, 1 upon lambda is equals to R. Now, in place of n is equal n1, you should always place 1 for Lyman. But for the longest wavelength, you should place n is equals to 2 here. Because this is the Lyman series for n is equals to 1. This is first transition and second. And the most one will be happening from infinity to 1. But you can see here, this is 1 upon lambda. So if this value increases, the lambda will decrease. So that is why we have taken the minimum value from 1 to 2 only. Although we can take it to 1 to infinity, but that will ultimately increase this 1 upon lambda. Increasing 1 upon lambda will decrease lambda because it is the inverse of this. So that's why for the longest wavelength, we should have the first transition. And for another reason also, if it is the longest wavelength, it will consume minimum energy. Longest wavelength having minimum frequency, and minimum frequency means minimum energy. Okay? Longest wavelength having minimum frequency, which is ultimately lead in minimum amount of energy consumption. So here you can also see the transition is happening from n is equals to 2 to 1. So very less amount of energy required in comparison to other transition. Now 1 upon lambda, you will remember that direct value is 1215 angstrom. Okay, you can do it for another series also. If you want to calculate what is the shortest series of Lyman, so or shortest wavelength of Lyman, shortest wavelength of Lyman series, which will also be termed as the series limit. This will also termed as the series limit. Okay. So for that, it's very simple. We want to increase the value of lambda. So that should be R into 1 upon 1 square. For that, you should place here infinity. It means that electron is transiting from the infinity state to the ground state. And that will ultimately lead you to the 1 upon R, which is nothing but 912 angstrom. This is the value of lambda. Lambda is equals to 912 angstrom. Now, for Balmer series, same procedure you have to follow for the longest wavelength. 1 upon lambda is equals to R into 1 upon 2 square. Yeah, it will start from 2 minus 1 upon 3 square. This is for the longest, and for the shortest, it is R into 1 upon 2 square minus 1 upon infinity. This thing you have to follow. The same you have to follow for the partial and effect. Okay. Now let's just move on to the next question. Here, in a nuclear fission reaction of an isotope of mass capital M, three similar daughter nuclei of same mass are formed. The speed of the daughter nuclei in terms of mass defect delta M. Now we know that delta M will travel with the speed of light, so this will be the delta M c square. This is the energy acquired by the mass difference. Now it has distributed among three daughter nuclei of same mass, which means we can say it will be having m by 3, m by 3 and m by 3 of mass. And let's say they are traveling with a speed of v square. Okay, so just take one of that, which is nothing but this is not 1 by 2 delta m into c square. Okay, now I'm giving you 1 minute to solve this question. Try to solve it out and let me know the answer. So I hope you have tried to solve it. Now, this delta m c square is nothing but the binding energy, okay, for the differential mass, or we can say the mass defect. And these are the daughter nuclei, so they will also have 1 by 2 mv square of kinetic energy. So all of that energy will be given by delta m c square is equals to 1 by 2 m by 3 v square plus 1 by 2 m by 3 v square plus 1 by 2 m by 3 v square. Now if you just multiply them, delta m into c square will become 1 by 2 times m v square. So this is 2 delta m c square upon capital M is v square. Now v will become square root of 2 delta m upon m into c. Okay. C will be outside of this because square is there. So this is the velocity that will be acquired by the daughter nuclei. Option C is the correct answer. Now this one. A monochromatic light of frequency 6 into 10 raised to the power 14 hertz is produced by a laser. The power emitted is 2 into 10 raised to the power minus 3 volt. How many photons per second of an average on an average are emitted by the source? So here we are given with frequency, which is 6 into 10 raised to the power 14 hertz. Okay. And power is given by power emitted 2 into 10 raised to the power minus 3 watt. Okay. And we have to calculate how many photons per second on an average are emitted by the source. Okay. देखो पावर हमें पता है पावर इज नथिंग बट द रेट ऑफ वर्क rate of doing work is the power, so itself it is per second. Okay, try to solve it. Given you 1 minute to solve this. Try to solve it out. So in this question, I hope you have tried it. Power is given to us, that is emitted by this laser. Now we know that one photon contains energy of h nu. Got it? Now n electrons contain the energy of nh nu. It's very simple. Now power is nothing but the energy emitted per unit time. We can say that power is nothing but energy emitted or the energy consumed per unit time. So if it is asking for per second, we can use that P is equals to E for per second. Now P is 2 into 10 raised to the power minus 3 watt. And we have to calculate H is 6.63 10 raised to the power minus 34 and nu is 6 into 10 raised to the power 40. No, 34 and 24 will become just the mathematics now. Minus 20. Now, this will become n is equals to 2 into 10 raised to the power minus 3 divided by 6.6 10 raised to the power minus 20. This will become 2 by 6.6 into 10 raised to the power 20 minus 3, because 20 will come up, so it become positive. 20 minus 3 will be 70. Now 10 we can also remove, removing the decimal here, decimal like this. So approximately if you divide it, it will become 10 upon 33 multiplied by 10 raised to the power 70. Now we also know that this will consume, it's approximately 3 point something times of this, and it will consume 1 power of it. So here h value is given to you this. So we can say this will approximately come as 5 into 10 raised to the power 15. Approximately come as 10 raised to the power 15. Okay. Hope you got this. Now, this one. The de Broglie wavelength of a photon and alpha particles are lambda and 2 lambda respectively. The ratio of the velocities of proton and alpha particle will be. Now we know that de Broglie wavelength is nothing but h upon p. P is nothing but the momentum of the particle, which we can also write as at m h upon mv. Now if h and v are constant, if h is constant, we know that lambda is directly proportional to mass into velocity. So we can say that lambda 1 by lambda 2, or we can say lambda of proton to the lambda of alpha is equals to mass of alpha, velocity of alpha particle, mass of proton, and velocity of proton, because it is inversely proportional. Now lambda of photon is given as lambda. Lambda of alpha is given as 2 lambda. Lambda upon 2 lambda. Mass of alpha particle, you should know that mass of alpha particle is 4 times of mass of proton. It comprises of 4 protons. So mass will be 4 times. We can write as 4 mp, and let's just consider the velocity. We have to calculate as v alpha mp into v. mp and mp will cancel out. Lambda and lambda will cancel out. So this will become 1 upon 8 is equals to v alpha upon vp. Okay. Now, what is the ratio between us? Proton to alpha particle. Just inverse it. So vp upon v alpha will become 8 upon 1. So 8 is to 1 is the ratio, which is the correct answer of this question. Anyone, if you have any doubt, you can ask. Now this one. In a photoelectric effect, experiment, a light of frequency 1.5 times of the threshold frequency. If threshold frequency is f0, the incident frequency is 1.5 times of f0, is made to fall on the surface of photosensitive material. Now if the frequency is halved and the intensity is double, the number of photoelectron emitted will be. We have half the frequency. Half of the frequency means the incident frequency will be 1.5 times of f0 divided by 2, which is nothing but 0.75 into f0. But I have told you in the beginning, to eject out the electron, at least we require this much amount of threshold frequency, of a incident light, but it is less than the incident light. So here, since the threshold frequency is greater than the emitting frequency or the incident frequency, then no electron will be coming out. So zero electron will be coming out because it is not crossing over the threshold of it. So no electron will pass, whatever the intensity is. Intensity is just told you about the numbers, number of photon or number of electron coming out. Okay, I just told you about the number, but frequency is something that talks about the energy. Okay, so I hope that you have understood it. Now next, this one. When a metal surface is illuminated by the light of wavelength lambda and stopping potential is 8 volt. तो जब wavelength lambda था तो stopping potential 8 V naught. When the same surface is illuminated by the light of wavelength 3 lambda, the stopping potential is 2 V, which means 2 volt. The threshold wavelength of the surface is. Now we know that the equation here is kinetic energy maximum is nothing but E times of V naught. V naught is the stopping potential. Stopping potential. No, but there is another equation also that maximum kinetic energy will be the difference of incident energy, that is actually divided by minus work function of the material. Now we can have here EV naught. We can write nu as c upon lambda because photon is traveling with the speed of light. So it's c upon lambda minus c upon lambda naught. Now, for the first case, when incident wavelength is lambda, although the lambda naught will not change for any of this, lambda naught is the material property, so it will not affected by the incident radiation. So for lambda, we can keep this equation number 1. But here the V naught will become 8 times 8. This is E into 8. For second equation, it will become 2 into is equals to Hc upon lambda will become 3 lambda minus Hc upon lambda naught. If you just subtract equation 2 from equation 1 or equation 1 from equation 2, 1 minus 2 if you will do, it will become 6E is equals to Hc by lambda minus Hc by 3 lambda is equals to we have to calculate the value of lambda naught, so we have to cancel out this lambda. Just multiply the equation by 3 here, just multiply it with 3, so divide it by 3. This is 3 and 3, and now subtract it from this, minus this will become plus. So 8 by 3 E minus 2E is equals to this, and this will cancel out. This will become Hc by lambda naught minus Hc upon 3 lambda naught. Okay. Now, so this will become 3 minus 2. 3 into 2 will become 6. So 80 minus 60 will become 2E upon 3 is equals to, this will become Hc upon lambda. We can take common Hc upon lambda now. 1 minus 1 by 3, which is nothing but 2 by 3. So 2e upon 3 hc upon lambda naught into 2 by 3. This and this will cancel out. So lambda naught here is coming out as uh, hc upon lambda naught is equals to e. This is the equation results we are getting. Now, we know that the maximum kinetic energy is the difference of the incident energy minus the work function of the material. Okay. And lambda naught here is the threshold wavelength of it, which is hc upon e is equals to lambda naught. Now, in terms of lambda, it is asking. So, in terms of lambda, how we can write it? देखो, lambda here is, if you will see, just a second, we can solve it here. Just give me 2 minutes. So here in this question, we have made two equations, equation number 1 and equation number 2. This is equation 1 we have made, and this is the equation number 2. Now, when we solve them, the lambda is ultimately coming out as lambda naught. In terms of lambda, it is coming out as 9 times of lambda. Okay. We have to solve these equation 1 and 2, and then accordingly we have to calculate the value of lambda. So this is it for today, guys. If you have any kind of doubt, you can ask. Otherwise, the lecture is being over. Thank you so much for being attentive and being responsive. Bye. Take care.